I begin by, after talking to Julia, we just split up the parts of the argument. So I'm going to finish the argument. And okay, it's been, it's kind of a technical argument, and we just had a 20-minute break. So this is kind of should be self-contained. So we have some polynomial rings. It's just a polynomial ring. I got rid of the epsilons, made it simpler. Just polynomial ring, and then a polynomial ring over that polynomial ring, which is just another polynomial ring where there's some variables that look like matrices, coefficients of a matrix. And then we have some relations that say that rho I times rho j is actually a linear combination of the rho k's, right? Because we're rho i's, because we're modding out by delta square, which is like any rho I times another rho j. And so, okay, so we have this this equation that tells us how to write any rho I times rho j as a linear combination of the rho k. And then we have some element, which I'm not going to go through. It doesn't matter. It's not going to matter for this talk, which is an R. The point is you want to show that its image modulo j lies in the image of the invariance. So its reduction mod j lies in the image of the invariance from R mapping to the invariance, under the Borel, mapping to the invariance of R mod j under the Borel. Okay, and so how do you do this? Well, this is just cohomology. You have a short exact sequence and you're taking invariance, so you get a class in H1. Okay, and as Julia mentioned, we're taking rational cohomology here. So rational doesn't mean rational numbers. It's like rational sense of rational functions. So it's algebraic group cohomology is maybe a better word for it. I guess some people call it Hochschild cohomology. I know there's different names for it. Okay, so our element E, which we, as Julia explained, we prove that it lives in here. So the first thing is an explicit computation, and you prove that it's invariant under the Borel. So it gives rise to a class in the rational cohomology. And you want to show that class vanishes because that means it's in the image of this map. Okay, so how do we show this class in H1 vanishes? Okay, so the first observation is, in fact, that to get the invariance under the Borel, you didn't need to mod out by all of J. There was a smaller ideal that you could have modded out by. So J was, all for like coefficients of this matrix. So rho I times rho j is the linear combinations of rows. And so you have an A coefficient, a B coefficient, C coefficient, and D coefficient in order, to say that a matrix is zero. You have to say all four entries are zero. But if you just look at the ideal generated by the B coefficients of these elements, then you get a sub-ideal, okay? And in our proof of invariance that Julia kind of outlined or given an example of, we only use the B coefficient ever in showing the invariance. So it actually comes from a different class, from a smaller ideal. And so therefore, the invariance there give you a class in H1. And so your class is in the image of the push forward because it's actually invariant under J prime. So your class pushes forward. So what we're actually going to show is that this push forward map on the H1 of J prime mapping to H1 of J is zero. Okay. So now there's R relations and they each have one B. So this is each of these matrices has one B coefficient. So there's R elements, which I'm going to call capital B1 through capital BR. So like it would, BI, if the first row is with I and J, then it would be like, how do you multiply matrices? AI, BJ plus, I don't remember how to multiply matrices. You know how to do this. the B coefficient of this matrix is B1, capital B1. Okay. All right, so that's just some notation. All right, so as Julia mentioned, the key idea here was using the Kosul complex. And I should say that the idea to do this came from staring at equations on a computer. So we had done these computations by hand that Julia did an example of, where we like manipulated the difference in the determinants. We got stuff instead of traces. Everything was either a trace or a determinant. We're very excited. How do we show that? Okay, and then we did that for R equals 3. Then we started doing R equals 4, and it was like a mess. We had no idea how to do it. We had no way how to organize the computations. So I had undergraduate visiting me from Barcelona, a student of Victor Rocher, was writing his senior thesis. And so I don't know how to code anything. So I said, hey, I got an idea. Why don't you code the R equals 4 case of this and see if you can split this cocycle? And he did. And he wrote it and he coded it. And he showed me the splitting things. And the splitting, it was like this long computation, like half a page. And it was just full of stuff like A1 times D2 minus D1 times A2, like just these wedge product things were just like showing up everywhere. It's like, aha, I've seen wedge products before because I went to grad school. So the Kosul complex. So I remind myself what it was. and it turned out that turned out to be the key. So anyway, so the point is, take classes in grad school that don't have to do with what you're studying, because it might be useful later on. So I'm very glad I learned this from Eisenbud. Okay, so all right, so the Koszul complex. So you have this free Z module of rank R, and you take sort of the wedge powers of it, and you tensor with the ring R, and then there's a natural map where you kind of split off a guy from the wedge product, and you view it as an element of R, and you kind of multiply it onto the R factor. Okay, and that's the Koszul complex. Okay, so it's a complex, so the composition of any two of these is 0. And then an amazing theorem in commutative algebra is that if the BIs form a regular sequence, okay, then this is actually exact, right? And so we can prove that the BIs do form a regular sequence in a polynomial ring, and therefore this is exact. And somehow it's very important that if you have exactly R elements, if you had R plus 1, it would no longer be a regular sequence. So this is a nice argument that's in the paper, that it's a regular sequence, and then you get the exactness of the Koszul complex. Okay, so how are we going to use that? So this is just a construction. Okay, so the idea is we lift our cohomology class. We're going to lift our cohomology class across the complex. So the image of F1 is just the ideal. So this is the free module generated by the BIs, and then they map under F1 just to BI. So the image of this map is the R module generated by the BIs, i.e. the ideal generated by the BIs, which is the definition of J prime. Okay, so the image of F1 is by definition J prime. So we have a class in H1 of the image of J prime. Okay, and so what I'm going to do is I'm going to lift that class in the H1 of the image of F1 to the H2 of the image of F2 to the image H3 of the image of F3 ... Okay, that's what's going to do in the next slide. So how do I do that? All right, so the image of F1 is by definition J prime, and so we have a class in H1 of J prime. Now the long exact sequence associated to this short exact, so you can take a long, if you have an exact sequence with many terms, you can split it into a bunch of short exact sequences, right? And so the splitting it at the first stage gives you the image of F2 is the kernel of the map from V tensor R into the image of F1. So the long exact sequence in cohomology associated to this short exact sequence gives me a class in H1 of image of F1, gives me a class in H2 of the image of F2, right? And so we're using the exactness in a crucial way here of the original Koszul complex, because we can split up that exact sequence into a bunch of short exact sequences. And so each step of the way, I just repeat, I have a class in HI, so alpha I, and HI of the image of Fi, and I just take the connecting homomorphism and I get a class in HI plus 1 of image of Fi plus 1. So you keep going, and at the end of the day, your alpha R plus 1, your R plus first class is 0 because the module is 0, right? So it ends. So we have alpha 1, alpha 2, alpha 3. They're in the HI of the image of Fi. The last one is 0. Okay. So what do we do with that? We still haven't really done anything yet. Okay. Now the point is, this fits into a commutative diagram. I haven't put J in yet, right? So the class in H1 of J prime doesn't vanish, okay? But its image in H1 of J is going to turn out to vanish. That's what we're trying to prove, okay? And the point is, there's a commutative diagram here, and I'm not going to be able to fully explain this except to say that, I guess I kind of can explain this, but so remember, the V's come from the B coordinates, and now the J, the difference between J and J prime is that J has all 4 coordinates, A, B, C, D. So you make a module, so you replace V by the module that has all of A, B, C, D, right? And then you take the wedge powers of that. So the wedge powers of the V obviously map to the wedge powers of something that contains V, that having all 4 A, B, C, D coordinates. And then you decompose the wedge power of a sum using the Kunath formula, and you extract from that a certain component in which these maps can be shown to lie. So that's a little summary of what we do, but basically there are modules WR where these maps lie, and the punchline is, when you take the particular components that these wedge powers lie in, they turn out, you can prove this in the computation, that they turn out to be sums of copies of the adjoint representation. And the reason that we care about the adjoint representation is that it turns out to be an acyclic B module. as trivial cohomology. Okay, so long story short, be an explicit computation, we can map this complex to a complex with modules that have trivial cohomology. Now, this bottom sequence is a complex, but it's not exact. Okay, so this is the setup. So all I'm going to need to use at the end of the day is that this is exact, and these are acyclic, and that the diagram commutes. Okay. So I let alpha I push forward, the push forward of the alpha I under this map, I call that beta I. And so the push forward of my first class, alpha 1, is the class beta that I've been trying to show vanishes all along, right? Trying to show this is the zero map. So I want to show that if alpha 1, it pushes forward to beta 1, it vanishes, okay? So now if you unwind what we've done, what does beta I plus 1 represent, right? It's a push forward of something that was under a connecting homomorphism. What do connecting homomorphisms give you? They give you the obstruction to lifting. Right? So beta I plus 1 represents the obstruction to beta I lifting to the term in this sequence. So, right, so the classes aren't in HIs of these modules, remember. They're HIs in the images of these maps. And similarly, beta I is in the image, HI in the image of GR, right? And so if you want to lift the class and the HI of the image of the map to the HI of the actual module, the obstruction to that would be what beta I plus 1 is. So now we can finish the argument. This is what Julia referred to. I call this a beautiful cascade. All right, so we have alpha R plus 1 is 0. So it pushes forward, okay, to beta R plus 1, which is 0, which is in the image of this map, okay? But what is beta R plus 1? Beta R plus 1 was the obstruction of beta R lifting to HR of WR, okay? But I just said beta R plus 1 is 0, so that means beta R does lift to HR of WR. But this is 0. This is an acyclic homology group. So if something lifts to 0, then it was 0, right? The only thing that lifts to 0, you push forward 0, you get 0. So something lifts to 0, it was 0. So beta R is 0. But what was beta R? Beta R is the obstruction of beta R minus 1 lifting to this cohomology group, HR minus 1 of WR minus 1. Okay, but this cohomology group is 0. So that means that beta R minus 1 is 0 because it lifts to 0. So it must have been 0. So they keep going down like this. They 0, 0, 0, 0, 0, and at the end of the day, beta 1 is 0. Okay. That's a general fact in homology. If you have an exact complex up here and an acyclic complex down here, then the push forward in homology down here is 0. And that it's finite and that it ends at some point. That is. All right, so that's the end of the proof that Julia was alluding or giving.
Sorry, can you repeat which module is the adjoint one that originally is acyclic that starts the whole chain?
These WRs are direct sums of copies of the adjoint representation, which comes from V being the B coordinate of a matrix, right? And then that's just one coordinate out of 4, and so you embed the V into the sum of all 4, and then you decompose the wedge power of that under the Kunth formula, and you get a sum of tensor copies of the adjoint. So it's not just the adjoint; it's I think tensor copies of the adjoint.
And these tensor copies of the adjoint are acyclic, like.
Yeah. So there's the whole category of modules called good modules that have a certain filtration, and that's closed under tensor products, and it's and the adjoint is in that category, and R itself, I didn't mention this, R itself is in that category. And so the tensor product of R with all these copies of the adjoint, they're all good, and all these good modules have trivial cohomology. So there's a lot of sort of theory of algebraic groups that goes into this cohomology algebraic groups.
I think we didn't mention the name of this invariant result also. People.
Oh yeah. So I guess that was in Julia's talk. She mentioned this fundamental theorem of matrix invariant theory. I'm not gonna be able to say the names. Processi and De Concini. Yeah, those are the names of it. There's an entire book on this, on that theorem. It's not, so theorem is not hard to prove over Q, but then we're doing everything integrally. Of course, the point is to basically we're trying to get all this is to prove something over F2. Really, that would be enough for us. But it becomes hard to do it over Z. So there's an entire book devoted to it. They define not just the relation, calculate not just the invariance, but also the relations in that group, in that ring. So it's a very nice book.
Sorry, just a quick question. Are you using that this is actually like like that this is really commutative, or were you using this as commutative? Like sort of, or were you using the maps on the bottom row somehow?
So the G's are, sorry, the betas are classes in the HI of the images of the maps in the bottom row, right? So the alphas were classes in HI of the images of these maps, not in HI of these modules, and so we wanted to push forward two classes in HI of the images of these maps, which is just the commutativity of the.
Okay, yeah.
Okay, so that's the end of that proof and kind of the end of the slide portion of this talk. So I'm gonna move to the blackboard and actually start talking about ETNC and kind of what our motivations were and kind of the fantastic work of so hopefully I'll have time to say what I want to say. I'll just stop when I run out of time. Okay, so my motivation was the explicit formula for Boomer-Stark's units. So this was my thesis. I should mention that ever since I got my PhD, every time I've given a talk, Henri has always like kind of gave me a needling joke about you haven't earned your PhD yet because I didn't prove this explicit formula for Boomer-Stark. So basically for 20 years, I've been trying to earn my PhD. So hopefully, Henri, you can say I finally earned it. Because that was my, thesis problem that, he gave me was to give an explicit formula or to prove an explicit formula for Boomer-Stark units. Okay, so, so one thing I realized, when I was a postdoc after I stated this was that there's a conjecture of Gross, which often goes by the name Gross's Tower Fields conjecture or the integral Gross-Stark conjecture, right? And so this was something that I proved in a paper in DMJ, I think it was in 2008. So I realized this kind of early on, without knowing how to prove either of these things, that there was this implication. And then this is a little bit anachronistic in terms of how my thinking goes about it, but to make the logical connection, we can say that the ETNC, maybe say some minus for the, there's a lot of words that go along with it, but for the minus part of the Tate motive associated to a CM abelian extension of a totally real field, I'll just call that ETNC minus, all those words. Okay, so this was known much earlier, due to, I don't want to give a wrong attribution. I mean, Burns and Kurihara and Sano and Popescu probably, all knew this. I don't know who came first, but this was kind of in the literature even before this. So this is predating this, I think. And then what, the recent result that we kind of realized, this is the work of Bullock, Burns, and Seo, and then kind of Meish and I and Jesse have a kind of take on what it is that they do, which is that my work with Mahesh on fitting ideals of Nabla theta, that this implies the ETNC. Okay, and so this is kind of, I think, the modern way to view like how we get this. I just should mention that kind of, like I said, this is a little anachronistic in terms of how I was thinking about it. We were actually thinking about this, I'll call it DK2, which is, a proof of this directly without accessing the ETNC, but that means that we were redoing the whole modular forms and Galois representations argument, but in a more beefed up way that allowed us to prove this conjecture directly. And in fact, in some ways, we kind of realized how to do this before we realized how to do this. Okay, so this is the timeline of how one thinks about it, how it actually should be thought about at the end are a little bit different, but that's just something I thought that I would mention. So in the time that I have left today, what I want to explain a little bit is this implication, and this implication. If I have time, seeing how much time I have. And this is a very beautiful argument, which was explained to me by Takamichi at some point. But I won't have time to give it, but I really highly recommending reading the paper of Burns, Kuhar, and Sano to explain that. But okay, I'll try to. So the point of this talk is I'll first talk about this, and then I'll try to talk about this in however much time I have left. Okay. So the idea behind proving that Gross's conjecture implies my explicit formula conjecture. It's going to be hard to give all the details because I don't want to give you this formula. Okay, but let me just tell you, like, what the proof of the implication doesn't really involve. It involves one particular functoriality property of the conjecture of the explicit formula that you can maybe believe, which is an analytic property. And then the rest of it is purely kind of formal. So let's just remind ourselves what the setting is. Okay, so F is the totally real field. H is the CM abelian extension. And G is the Galois group of H over F. Sorry, my wife is calling. Okay. Let's see. All right, and then so S is going to be, actually, you know what? I'm going to slightly alter notation if you don't mind, because it'll be useful for when I talk. The point of what I'm doing now is to state Gross's conjecture, by the way, in case you're wondering what I'm doing. To state Gross's conjecture, is what I called S before, I'm going to call R, if you don't mind. This is primes ramifying in H union, the infinite primes. And then T is just some finite set disjoint from R, satisfying some conditions that I don't want to state. And then, of course, we have the Stickelberger element. With that data, we have, so this all gives some theta sub RT, which is the Stickelberger element. I don't want to redefine it just so I don't take too much time. Okay. And then we take a P, which is not an R union T that splits completely. In H, so it's a prime ideal of F. And then there's a map that we're going to define. Oh yeah, and then we fix a Gothic P of H above this lowercase Gothic P. And we define a map for anything in H star. We define ord sub G of U to be this element in the group ring. Given that just encodes the valuations of U at all the primes above P, or equivalently at P, the conjugates of U. It's equivalent to this is sigma and G. Okay, so this is just some element in the group ring. Okay, and from the Brumer-Stark, so restating the Brumer-Stark conjecture from this notation, that there exists U and H star, which stops the value of U is 1 for all W not dividing P, U congruent to 1 modulo all primes in T. Okay, that's all the lawyer stuff. Such that ord sub G of U is theta. Okay, that's the Brumer-Stark conjecture. And so my W there includes all the Archimedean places. So it's complex apps of value 1 at all complex places. Okay, so that's the Brumer-Stark conjecture that we, I guess, now have proved. Okay, so what is Gross's conjecture? Gross's conjecture is a refinement of this. Okay. So Gross's conjecture. So now we pick a finite abelian extension of F. Containing H. Okay. And we have some notation, which is the Galois group of L over F. So instead of writing it out, it's better to just draw a picture. You have L, H, F. Oh, pretty low. Right. And so this Galois group is G. I'm going to call this Gothic G, and then I'll call this gamma. Okay. So the Galois group of L over H is gamma. And we already know, right? And so G mod gamma to G. Okay. Then the relative augmentation ideals. So we've seen a lot of augmentation ideals in the past week, but this is the relative augmentation ideals, the kernel of E bracket G to Z bracket G. Because Gothic G maps to regular G by reduction. Okay, and then we're going to note, so we're going to now let S be R union P. Okay, this implies that LST of chi at S is just 1 minus chi of P norm of P to the minus S LRT of chi, which in particular implies that LST of chi at 0 is 0 because this Euler factor is 0. This is called a trivial 0. Okay. And so this statement means that this theta st is in I. Okay. Theta st is the element such that when I apply chi to it, I get LST of chi inverse of 0, which is 0. So what's the element that whenever I apply chi to it, I get 0? It's 0. So sorry. Sorry, I should say this is LST of oh, sorry. Let me. I said too many things at once. This implies that LST of K over F, H over F,
L over H over F. Yeah.
H over F. Right. So you didn't know what I was going to say, Christian. This is 0, right? And that implies what I wanted to say here, which is that LST of L over F is an I. Sorry, I tried to say too many things at once. Right. The fact that all the L functions downstairs for characters, so this is characters chi of G. Right. This observation here. Right. And the reason that this is 0 is because P splits completely. So its Frobenius is trivial. So chi of P is 1. Right. So this is 0. Okay. For chi being a character of G, which means that the theta function, the theta function of H over F, the Stickelberger element of H over F, I should say, is just 0 because all the L values are 0 that you're interpolating. What is the reduction modulo I of the Stickelberger element of L over F? It's just the Stickelberger element of H over F. So it reduces to 0, which is the definition of being an I.
You also want L over F to be unramified outside of.
Yes, I did not say that, and I should have. Thank you. Otherwise, you can't really talk about this in this way. So L is unramified outside S. Thank you. Otherwise, so one thing that's nice is I'm allowing ramification at this Gothic P in S. Where's the definition of S? Is it covered? Yeah.
Here.
There it is. Yeah, S is right. So I'm allowing ramification at this P in L. Okay, so that's the setup for Gross's conjecture. Is just to note that this Stickelberger element is contained in I. And then the conjecture is about the image in I mod I squared. Okay. Okay, so so just like we defined ord G, I'm going to define rest G now. Okay, so this is for anything U and H star, we can define rest G of U be the sum so I'll explain this tilde in a moment. Okay, so what's going on here? So where rest of Gothic P is the local art and reciprocity map. Well, okay, let's just view it as that, it's a local art reciprocity map, but we can view it inside the global Adels, and then it's just the usual reciprocity map, global reciprocity map. So this is a Galois group of an abelian extension of H. So there's a surjection from H star onto it. I think that's the reciprocity map. Okay, and so this is, and so of course H, H is just embedded in here. So you can evaluate it on any global elements. Okay, so you get an element of gamma. Okay, so
Minus
say it again. Yes, thank you. Yes, think. Okay, right. So this is something in sort of I gamma, right? It's in the I mean this is something in I, right? It's in I because this is in gamma. So multiplying, but so subtracting one, it goes to 0 when I one out by gamma. So so obviously this whole thing is in I. Makes sense in I. And this is any lift of sigma, okay, to script G. And it doesn't matter what lift I take, because if I change it, I multiply by something in gamma. And of course, if I multiply something, right? So the difference by taking a different lift will give me something in I. And if I multiply by something in I, to get something in I squared, right? So this is well defined mod I squared. Okay, so this is well defined mod. So sigma tilde, any lift. Sigma G. Okay, the Gross's conjecture. Well, now I've set everything up. You can probably conjecture guess what it says. It says that rest G of U is equal to this theta. Okay, so I have two elements of I mod I squared, and so this is like a leading term conjecture, right? I mod I squared is like taking derivatives of functions, right? Looking at something that I mod I squared. If you have a variety and you have a local ring at a point, then this kind of looking at derivatives of functions to that point is the image in the maximal ideal modulo square. So that's the kind of intuition behind this. And this is kind of like a regulator. This is like log p of a unit. And this is, of course, like the derivative of the L function, right? The L function vanishes, so it means to be in the ideal. So you're looking at its derivative. So it's like saying the derivative of an L function is the log of a unit. Yeah.
You reach the Brumer-Stark.
Yes, for the Brumer-Stark unit. Yes, not for every use. For right. So when you choose the unit that satisfies this, right? When you choose the unit that satisfies this, then you get this. That's a very clean projection. By the way, for those of you that like L invariants, I'll just say if you quote unquote divide these, you can't because they're right. If you divide, this by this, you get a log of U over ord of U, and then you get a derivative divided by a value, right? It looks like very much like Greenberg-Stevens, right? That invariant equation. Okay. And in fact, I mentioned this DK2 paper. This is our Duke paper. We make sense of that ratio in an algebraic way by creating a ring in which there's a ratio. So, okay. So what did I want to say? Oh my God, I'm almost running out of time. Okay, I'm gonna have like 10 minutes to say something about ETNs to get this right. what did I want to say about Gross's conjecture is that Gross's conjecture implies explicit conjecture. I'll say this very okay. I'll just say this in a few words. So I do want to spend some time talking about these. Okay, so Gross's conjecture implies explicit formula. For the idea. Okay, so what kind of extensions can I take for this L? Okay, so if you add, so what we're going to do is we're going to add, and this is an idea that I got it when I was a postdoc at Harvard from Richard Taylor, which is, I mean, he just asked once, it wasn't an idea, it was a question, and then I gave a seminar talk, and then he walked out of the room, and I was like, and I thought about that one question for like a year. The question was like, what happens if you enlarge S? And then he walked out. And then I thought about that for a really long time. So that was the key idea. So take my old S and then add a prime Q. Okay. And right, so what type of extension can you take? And in fact, because we only want to look at, say, p-adic formulas, we only want to look at kind of just tame ramification at Q can give me a big p-adic p, say like a z mod p to the n, right? Just the tame part. So what we can imagine is, let's just take in my example, just to make things simple, let's like take this to be the narrow Hilbert class field. Just do an example. Okay, and let's take this H to be, say, I'll add a bunch of ramification at P, which I'm allowed to do, and I'll add some ramification at Q. So this is the narrow ray class field of that conductor, okay? Class field of conductor P to then Q. Okay, and then what does my class field theory say? So this is what I would call gamma in my picture, right? That's my L, right? I'm gonna take L equal to that. Okay. And what is my gamma? My gamma, according to class field theory, is, what is it? Hope I get this right. O mod P to the n star cross O mod Q star modulo the totally positive units. I just call it OF star greater than equals 0. And then, the reduction of them in here, right? The reduction of them in that, right? Totally fine. Okay. And so the point is, if I want to get so the reciprocity map is giving me a formula for the unit in here. Okay, so I didn't say this. Okay, what is I mod I squared isomorphic to? I should have said this. And I think this came up in Julia's talk. It's basically gamma tensor D bracket G. So it's basically a bunch of elements of gamma indexed by G. And so what Gross's conjecture is for basically the image of the reciprocity map of U in gamma and all of its conjugates. That's what this extra thing is doing. And you're getting a sum over all the conjugates of U of what the image of those conjugates are in gamma under the reciprocity map, right? So that's basically telling me the image of gamma in here. And what am I looking for? A p-adic formula for the unit. I'm looking for the image of the unit in here. And the problem is, before you put in this Q, this unit is eating up this space. If this Q wasn't here, you'd be getting from Gross's formula an image in O mod P to the n star modulo this annoying unit. For example, if this is a real quadratic field, there's some unit, and it's just going to eat up almost all of this, right? Even as n gets bigger and bigger and bigger, it's just going to keep up eating almost all of it, and you're just going to get some finite piece of information. And there's a lot of computations from Gross's conjecture before this idea came along of like how many, like if the unit happened to be congruent to 1 mod P or 1 mod P squared, then Gross's formula is giving you a formula for the unit mod P or mod P squared. And there were some computations that were done by Dave Dummett of these Stark units using Gross's formula, what they were mod P and mod P squared, mod P cubed in cases where you took P to be the divisor of the fundamental unit -1. So, okay, now this idea, just spurred by Taylor's question, what happens if you expand S, is now if you throw a prime in S, what you can hope, so choose Q such that epsilon is in OF star greater than 0, then epsilon congruent to 1 mod Q implies epsilon is congruent to 1 P to the n. Okay. And now to actually do this in practice, you need more than one Q probably. You probably need a bunch of Qs. If epsilon is congruent to 1 module all of them, then it has to be congruent to 1 module. Okay. Okay. Right. Okay, and why does that help? Because what does Gross's conjecture give you a formula for? I said it gives you a formula for U, but now I have a product for U in here, but I have a product that gives you a formula for U comma 1. Gross's conjecture gives a formula for the pair U comma 1 in mod P to the n star. Okay. And then what you need to prove, the one analytic thing you need to prove about my conjectural formula, so I need to show that in my conjectural formula, that this is the same thing that Gross's conjecture formula gives you. That this is congruent to theta st of L over F in.
Do you not want to mod out by global units there? Gross's conjecture to this first line.
Oh, thank you. Sorry. Of course, yes. That's sort of the point. It doesn't give you a formula in here, otherwise you'd be done. It gives you a formula in the quotient thing, right? So what we need to show is what you need to prove. This is a purely analytic statement. This is some p-adic integral. This is something with an L function. This is all analytic. There's no algebra here. So what we need to prove is that my analytic formula, that if you put a 1 in the second coordinate, then you get actually. So that's an analytic computation that works out. Okay.
Reciprocity of U.
Yeah, but I mean, that's what I mean. But I mean, reciprocity of U, and then you undo reciprocity under this isomorphism. So it's really U, right? It's what the U is mod P then, right? You're kind of taking reciprocity and then untaking reciprocity. But yeah, I mean, maybe there's some normalization because U is a unit, but okay, project it to, okay. All right. So once that's true, okay, then we get, so then once you've proven Gross's conjecture, I mean, then Gross's conjecture implies that the Brumer-Stark unit, which I'm calling U1, is equal to the conjecture for it in this quotient space. Okay. Which means that the ratio is trivial in this quotient space. Okay. But now you see that, okay, if you have these two things being equal in the quotient space, that means they differ by an element of here, which is embedded diagonally, but these both have a 1 in the second coordinate. So a unit that's 1 in the second coordinate is also 1 in the first coordinate by this assumption. So this implies that U is congruent to U conj mod P to the n by choice of Q. So that's how you prove that Gross's conjecture implies my explicit analytic conjecture. There's one purely analytic thing that you need to check, and it's this congruence. Okay, so it's maybe not surprising, purely analytic things with L functions you can check, but
And this condition on Q, I'm assuming it's a Chebotarev.
it's a Chebytarov, yeah, yeah. There turns out to be some assumptions. You need to show that, you know, your prime P is, you need to choose P to be unramified enough or something like that to get the Chebytarov conditions to not be contradictory to one another.
This is a Taylor-Wiles.
It's the Taylor-Wiles, yep, yeah. I mean, this is, yeah,
why.
that's why Taylor suggested it. Yeah. Okay. So that's the end of that implication. And then in the last, I'll say 15 minutes, give me an extra couple minutes, I'm gonna say something about the ETNC. Okay, so what is the statement that so this is like a changing gears now. So we put on our fitting ideal Rumor Stark hats again. So we get some kind of formula like the fitting ideal of Nabla, that's T of H minus equals theta. And what is one defect in this statement? Okay, yes, the ideal generator, right? Okay, so why is this better than just like the main conjecture? It's because it's equivariant and integral over the group ring, right? You don't break this up into characters. You're proving something really integral. That's a statement of all the characters at once. Okay, so that's why it's kind of ends up having stronger implications than just the main conjecture does by itself. Okay, so but there's a flaw, which is that in order to get something for all characters, we have to sort of fix some S here, right? We have to fix some S. You would include all S, all places that ramify in G. I mean, in H, sorry. So, right? So if any prime ramifies, right, then we have to include it in S. But it could be the case that the entire decomposition group, so even though the inertia group is non-trivial because it's ramified, the entire decomposition group, right, the fixed field, the decomposition group could be some other field here. So E, fixed field of the decomposition group could be some other CM abelian extension, possibly, right? And then you could have characters that factor through this, on which this prime that you've included in S, the decomposition group is trivial, right? And so for the same logic that I made before, so say chi of GV is 1. So if chi vanishes on the decomposition group at some V, then LST of chi S, well, let's say chi S, this is the same thing I did before. The point is, it's unramified. I can take it out of S. Right? The only, rule for S is that it had to contain the ramified places. But now for this extension, for this character chi, it factors to this extension. It's unramified. This is, times an Euler factor. Okay, but I'm assuming that chi of the whole decomposition group is 1. So this is 1. So that implies that this Euler factor is 0 at S equals 0. So that implies that LST of chi at 0 is 0. So on the projection of this, so Z bracket G, projects under each character of G. I can apply it to an element of Z bracket G. Each projection, this is 0. And it's not hard to show that the fitting ideal of this is 0 too. It's the projection of this is infinite as zero fitting ideal. So you're proving 0 equals 0 under those characters. And that's obviously not ideal. That's clearly, you're not getting as much information as you could, because the point is that for the extension E, we have a statement where you take the V out. Right? This is in G, how to say, mod GV. I mean, is it the Galois group of E? Galois group of E over F. Right? So this is in okay. And so this is kind of recovering some non-trivial information at the character chi, because now chi of this is maybe not 0, and this has some interesting module there, and you're actually stating something. Okay, you're not just getting 0 equals 0. But now that's the whole point, is you didn't want to have to take different statements for different projections. That's what the main conjecture was. That wasn't good enough for you. You wanted something that was equivariant. So you really want an equivariant statement that sees all the characters and is non-trivial, even if there's a prime V and S that's split for a certain character. So you want to kind of package this and this together simultaneously in a way that you have information that's equivariant, so it's compatible. So you want to fit this together and this together. So that's what the ETNC is. So maybe I'll only have time to say it, state it, and then say a couple words about how one proves it. Needed one more talk, I guess.
You can take mine.
Okay, so it's annoying that these don't fit on the rim. Still, so the right, so the statement. Okay, so to understand how to make a statement that combines these, you have to not talk about ideals, but talk about elements. Okay, so we want to get rid of the parentheses there. So what was nabla? So you may remember that nabla was defined via a certain presentation, which under our assumptions is quadratic. So there's two, right? And so there's the kernel here, but I don't need that for what I'm about to say. Okay, so the punchline is somehow, so if I have the S, let's call this SH. Okay, well, SH means I take the ramified places in H and the infinite places and nothing else. Then if I have SE, this is the way I'll call this BH. Right. So I want to kind of connect these two in some ways. And so then the proposition that you can prove, right? So these are both, I mean, I guess at least on the minus side, these are both free modules of the same finite rank. And the proposition is that if you take what do I want to say, Galois coinvariance, right? Of what is, I got to give this Galois group a name. This is, what should I call this? Somebody give me a letter. J, I don't know. What's a good letter for a Galois? Okay, the Galois covariance under J, that this is my B. And same thing for B. By the way, I should mention something that we actually only realized when the referee pointed it out. Is that actually the fact that this is free on the, on the minus side. Everything here has to be on the minus side of being a little bit sloppy. I mean, it doesn't have to be, but for what we can prove, it has to be on the minus side. Is that actually the freeness of this was actually a conjecture of Kurihara. We thought that it followed. I mean, so it was locally free, but somehow that didn't mean that it was free, but it actually follows from our result that from our work that it's free. So let me just talk about this in that way, assuming that it's free. Okay, then so okay, minus. Okay, so what's that? V. Sorry, of course. Well, I guess it's true that it's for B because they're free of this, but yeah, that's not what I meant. Okay. So what this what this means is that if you take a basis for this module and a basis for this module, then that induces canonical modules here. You just take kind of their images modulo, modulo J. Okay, so basis. Right, by taking coinvariance. Okay, and that allows us to to state this form of the ETNC, and I should say that as we heard from Owen's talk, I mean there's fancy versions of the ETNC using derived categories and other, using determinants of complexes, but there's a very down to earth version of Kuihara, which is the one that we use here. Okay, which is that fix. Okay, so there exist bases for VH minus and VH minus such that the determinant, I should give this a name, FH minus FE minus, that the determinant of FE minus equals theta E F. Okay, for all CM E contained in H, where this is taken with respect to the induced bases. Okay, so for E equals H, this is saying that there exist bases such that the determinant, so there's no ideal anymore. It's an actual equality of elements of the group ring. The determinant is equal to theta. So, I mean, that just follows from, once you have this equality, this is the ideal generated by the determinant, right? That's the definition of this. So once you have the ideals being equal, you can pick the bases such that you can change your bases by units to get an equality of elements. And they're saying once you've done that, then if you take the induced bases for VE minus for any subfield, then you get an equality here. So somehow there's a compatibility between the units that are implicit in this equality and in this equality.
But what are your sets SE and SH here?
S is the minimal set you need to take. It's the set of primes ramifying in the extension together with the infinite primes.
SH and SE are different, right?
Yes. That's the point somehow. But
Is it really true that BH base change gives you BE? It should be a direct sum and not exactly the same.
BH is constructed out of this large set S prime.
yeah, no, the H and the E and the VH and the BH and the VE and the BE don't depend on S in some way. You take some large set S prime, which satisfies some conditions on the triviality of some class group, and these are free of rank S prime or the size of S prime minus 1. Right.
But you pick the same S prime, an S prime that
Yeah.
works for all the.
There's an S prime that works for all of them, and then the V. So what's different is the map, right? The map changes.
Oh, okay, because I was wondering.
The map depends on what S you're taking.
They changed the exact.
Yeah. So the most natural thing, if you actually wanted to make a commutative diagram, you'd have a problem because you have different sets here. But I'm not claiming any commutative diagram. There's no vertical arrows here. So the point is this map is different between here and here in the behavior at the primes you've excluded. So the map is different, but the point is these modules are the same. Like these modules kind of don't rely on the set S you take. The map does.
Those F's and FHs are at
Say it one more time.
no, I think those F should be over this arrows, right?
Oh my good Lord, yes, sorry. Thank you. You're right, I'm sorry.
Hold on, how are you writing down this isomorphism of the T's and the B's if you don't?
There are no arrows, but there's an isomorphism.
Yeah,
There's no commute, there are arrows, there's no commute, I mean,
Commute, you just.
well, I don't know what I mean. I mean, this is a mod, I don't want to put an arrow because this is a module for a bigger group than this. I'm just saying that the covariance of this is this. The covariance of this is this.
And it's not induced.
It's not induced map. It's not a. The behavior of this at the primes is different. Okay, so I thought I was going to prove the conjecture for you, but I've only had time to state it. So maybe Dominic could take some time to. Okay, so I'll just say a couple words about it. Maybe go 1 or 2 minutes over. So the point is, yeah, we have inequality. So let's say we've normalized it so we have an equality of this determinant with this theta. Then okay, you have some unit such that this determinant, the determinant of FE is equal to this theta times that unit. And what can you say from the behaviors? This gets to this question. What can you say? You can say, okay, so let's say I have a det of FH minus equals theta SHT, right? And then let's say that I have det of FE minus equals theta SE T times some unit. Okay. I mean, you have to worry, you don't necessarily know you have units because there could be zero divisors, blah, 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 but let's just pretend it's a unit. Okay. And well, what can I do from this? The problem is if you've excluded some prime, right? You've excluded some prime, then what you can say, if you kind of reduce this equation into this group ring, then what you get is somehow that det of FE minus times the Euler factor at this prime that you've excluded, which may be 1 minus sigma v, is equal to theta st. Sorry, so it is equal to theta se. Basically, what you want it to equal times the same Euler factor. So you actually get what you want, but this is exactly what you were getting at, I think, is somehow that like it's not commutative. And so when you reduce these Euler factors that you excluded, the things that were zero are okay. And so the point is somehow now this is a zero divisor, so you can't cancel and get what you want. Okay. Now the basic functions, I'll say one word about the proof, which is like maybe it's in a group ring case, but if you were to think of it in a polynomial case, it's as if you had an equality, right? In some ring like this. Imagine your grouping is like this. So this actually is the case if you have a cyclic group or something, right? Then if you have that kind of t, which is a zero divisor, times some x equals t times some y, right, in here, right, you can't conclude that x equals y, unfortunately. Which the punchline is you do get that x is kind of congruent to y mod t to the n minus 1. Right? And now I guess Taylor's suggestion rears its head again. The idea is you just take bigger and bigger and bigger field extensions in which you can kind of take n to infinity. So then if you get this congruence modulo all n, then in fact you're getting x is congruent to y. So another way of saying it is if you take it in the inverse limit, then you get this is maybe a more conceptual way of saying it. Then you get an equality in ZP double bracket t in which t is a non-zero divisor. So you can cancel, right? And then you get x equals y. So that's kind of a nice trick. If you have something where it's a zero divisor, you can put it inside an inverse limit where it becomes a non-zero divisor and you can cancel. Okay. So that's some sort of class field theory. We use I guess I'll just mention, we'll use the Grunwald-Lang theorem to construct the extensions that we need in order to get the prescribed ramification, the prescribed structure. All right, thank you.
Questions?
I think it's a bit late to ask this after the last lecture, but why do you, what's the intuitive reason behind taking the minus part everywhere? Why do you, is it just for technical?
No, it's fundamentally important. I mean, the plus part gives you you know, we don't know anything about the Stark units there. It's like if you take a, say, a totally real field, like a real quadratic field, and you take up even character, then its L functions at 0 have order of vanishing 2, because, you know, both real places split in this extension. And then you're getting determinants of logs of units. And this is the Archimedean Stark conjecture. So there's no, they're not P units, they're actual honest units. And we have really no way of sort of accessing those kinds of conjectures. So yeah, I can't really say anything on the plus side. So,
There is something else. So theta itself, which is the value at 0, lives naturally on the minus side of the group.
right.
So it's not gonna see the plus side of nabla or any other model.
Right. A way of saying it is that if you project theta under a character that's not totally odd, right? If it has any real place stays even, then it will vanish, right? The order of vanishing is the number of real places that stay real. So if you have even one, then the L functions will vanish. So you can't really say anything else. And then you're getting derivatives of Archimedean, you know, L functions and related to Archimedean logs of units rather than p-adic stuff that we could deal with cohomology.
But just in your statement there, I don't think you need the minus parts on the left hand side because the fitting area lives on the minus part as well.
Yeah, I don't think I need the statement here. Yeah, I think both is 0 on the plus side. Yeah, so I think I said it like I don't need it, but yeah, whatever. Yeah. Yeah, they're both 0, but it's 0 equals 0, right? There's interesting statement to be made on the plus side. We just don't know how to prove it. Yeah.
One question. In this analytic formula that you have, it is easy to see why you get all these ones, or what is the idea why in your
Okay, it comes down to a trivial 0 of an Euler factor somehow. I mean, like an Euler. So somehow when you project onto that component, then somehow you're not seeing the P stuff anymore. And so it's like you're how to say, you're projecting to a place where P splits complete, you have a field where P splits completely, and that's giving you a 0. So it's a trivial 0 phenomenon, the 1. Yeah, you have to look at the actual computation, but it boils down to that trivial 0. Yeah.
I think I misunderstood something in fundamental in the proof of Gross's conjecture, because it's
I don't think I stated the proof of Gross's conjecture.
well, what the
I
implication?
proved that, yeah, the Gross's conjecture implied my conjecture, yeah.
Yeah, because I mean, the Q that you were picking was dependent on n, and everything that you proved was modulo p to the n. So at some point, like is the implication only modulo p to the n, or do you at some point lift it?
Well, you do it for every n, so you get an equality. So you're right. So
But the Q is still dependent, is what I mean.
what is that? The
The Q
Q?
is still dependent on n.
Right. So for each, and if I want to prove there's something I didn't say, which I need to say, you're right. But let's say I want to prove 2 things are equal, I can prove they're congruent modulo p to the n for any n. Okay, so now I fix an n and I choose my Q. But the thing I think you're alluding to is the fact that the unit and everything will change now that I've introduced Q into my set S. So yeah, you choose a prime Q that modifies the unit in a computable way. So for example, in the paper, we just take Q to restrict a complex, Frobenius to restrict a complex conjugation in the field. So that has the feature that it just takes the Stark unit to its inverse, complex conjugation, right? So then if I hit it by the Euler factor at Q, which is 1 minus the Frobenius at Q, that just squares it. So then you get a congruence between 2 things squared. So as long as P is not 2 again, right? then saying 2 things are congruent mod P to the n's, their squares are congruent mod P n means that they were congruent mod P to the n.
Okay. So
Up to it like a little root of unity. Right. So in my original proof, we had like a root of unity ambiguity for this reason, and Matthew sort of got rid of this. So.
yeah, thank you.
Yeah, so I think that was the confusion you had. You're right. Adding Q changes the unit, but you make sure it does it in a controlled way.
Any other question? If not, let me remind you that there's a public lecture by Christian at 6 on the ground floor in room G03. Right? At 6 o'clock. Okay, thanks, Samit.